Good morning, and thank you to the organizers for inviting me to speak with you today. I'm sorry that I can't be online with you in real time. It's amazing how technology has eliminated the space between us when it comes to teleconferencing, but we haven't found a way to tackle the time zone difference yet. Well, I promise next time I'll be in person with you in India. So we all know that air pollution is a global public health crisis, and addressing this major issue is complicated by the fact that the response to natural and human emissions is complex and nonlinear. So the processes of meteorology, gas phase photochemistry, cross-boundary transport, thermodynamics, and what I'll focus on later in this talk, multiphase chemistry, all of these processes are not completely understood and highly nonlinear. And therefore, it's sometimes difficult to trace air pollution observations back to the emissions that they originated from. Our community's approach, and my group's approach as well, has been referred to as a three-legged stool, consisting of field and satellite observations of atmospheric composition, laboratory and theoretical studies to understand the fundamental processes that are taking place on a microscopic level, and what I argue is the main product of our community, large-scale models of atmospheric chemistry and climate, which can be used to prove our deeper understanding of the atmospheric system and also predict future scenarios, whether under climate change or different policy scenarios, etc. In my group's focus, my individual research group has largely been on this axis. I'm originally a laboratory scientist, but I have really been tackling the problem of how to bridge the scale between the molecular level information that we obtain in laboratory or theoretical studies and the complexity that can be contained in large-scale models. And we use process modeling, among other tools, to address that. Lately, we also have become involved in field and satellite observations through our participation and leadership in the Clean Air Toolbox for Cities initiative at Columbia. So I won't have time to give a full presentation on the Clean Air Toolbox for Cities, but I thought that some of you may be interested in it. If you'd like to learn more, you can look at our website or contact me. So this initiative is, although many of us have been working on issues related to air pollution in the global south for years individually, we grouped together to collaborate within the last year or so. And it's a highly interdisciplinary group representing 23 or more research groups across campus at Columbia, from our law school to data science to public policy, to engineers and environmental scientists like myself, to our School of Public Health, which is quite well known for its environmental health science. We're still in the pilot stage of doing some early studies and raising funds for our work. We're quite active in sub-Saharan Africa, as well as doing some work in India, mostly focused in Kolkata. And the pilot activities largely focus on closing the data gap that exists in many places with severe air pollution problems to help understand the magnitude of the problem, its economic and health impacts, the sources of pollution, and therefore motivate further climate action. I think the biggest strength of the Clean Air Toolbox for Cities project is our deep partner network, from global partners such as World Resources Institute and EDF, to local partners in Africa and local partners in India, including many of your institutions. We're very grateful for the opportunities we have to work side by side with all of you to unravel these issues in India and elsewhere. Okay, so moving on to this idea of multiphase chemistry and how do we bridge the scales between the molecular level and global models. So as these length scales increase, the complexity of the models increase. So more processes need to be included once we get all the way to climate models. Besides atmospheric chemistry, they need to include processes such as radiative transfer, even ocean circulation, meteorology, etc. So they're quite computationally intense. And therefore, even though each particle in the atmosphere contains tens of thousands of unique chemical compounds, and we know many, many reactions that they're participating in, it's simply not possible to just dump all of that complexity into the large-scale models. And there comes a need to reduce that chemical mechanism for practical reasons, and we hope to have reduced chemical mechanisms that are as faithful to the fundamental chemistry and physics as possible, so that we can have high fidelity in the models. And tackling this problem is challenging technically. Also, it's a communication problem, and it's something that my group has been digging into for the last 10 to 8 years, I would say. We're focusing on multiphase chemistry, which that's jargon in the atmospheric chemistry world for chemistry that's occurring in the atmospheric aqueous phases. So what is that? That means fog droplets, cloud droplets, but also atmospheric aerosols, which are a bit hygroscopic and have some water associated with them, which is most of them. So, and I'll also note that this type of chemistry is quite important in this region where you are. So fog is known to be quite important for influencing air quality in the Indo-Gangetic Plain. And of course, you're in a mountainous region, so fog and cloud processing is of interest. So I'm glad that I'm able to speak with you about this today. So recall also that this is a dynamic system. Aerosols act as cloud condensation nuclei and fog nuclei and take up water to grow into cloud droplets, which then may evaporate and leave behind low volatility material in the aerosol phase. In some places, this cycling occurs very rapidly, many times per hour even. But no matter what life stage of the aerosol cloud cycle we're in, there's an opportunity for water-soluble gases to dissolve into the aqueous phase and undergo aqueous phase reactions to transform the composition of that phase and alter the loading of PM 2.5 in the region. So this is critical for secondary aerosol formation. Both inorganic secondary aerosols, so specifically sulfate, when SO2 is emitted through this combustion of fossil fuels that are high in sulfur, like coal, this along with uptake of ammonia and nitric acid is kind of the classic secondary inorganic aerosol formation family, producing ammonium sulfate, which is a very typical continental aerosol. This is also critical for the formation of organic aerosols. So when the water-soluble gases are oxygenated volatile organic compounds, then the associated aerosol that's formed is secondary organic aerosol. And this family of processes can be referred to as aqueous secondary organic aerosol formation. So the workhorse of my group is a process model that we developed called the Gas-Aerosol Model for Mechanism Analysis, or GAMMA. And this 2012 paper here is the original reference for that model, although we've continued to develop it through the years. You can think of this model, which we, in the lingo, it's a zero-dimensional photochemical box model. You can think of it like representing one grid box of a large-scale model and neglecting the transport processes and other complexities that come along with, let's say, a large-scale model, which frees us up to focus on the details of chemical processes and mass transfer. So within our box, we represent emissions and deposition of chemical species, their transport between the aqueous and gas phases, and then reactions in both phases. The fundamental equations that describe these processes are not something that we invented. They're classical physics that was probably first outlined in this form by Dankwarts. But what's new is the chemistry that we're able to represent in the model. So it was first identified in the early 2000s that aqueous phase processing was likely a very important source of secondary organic aerosol, and that for SOA to be represented correctly by large-scale models, especially when it comes to the vertical profiles, they really needed to include multi-phase processes. But the problem was that there was no numerical machinery to make that happen. And so we started tackling this problem at the process level with GAMMA. Okay, just a conceptual map of what GAMMA focuses on, which is this aqueous phase processing of oxygenated volatile organic compounds. So remember, the atmosphere is an oxidative medium, and any volatile organic compounds that are emitted are oxidized, and their products are generally more water soluble than the parent compounds. And according to their Henry's law constants, which in some cases are extremely high, like glyoxal, or they're more modest, as is the case for most aldehydes, they partition into the aqueous phase, where they can undergo a number of different chemical processes. The three families of chemical processes in the aqueous phase are self-reactions and hydration. These are processes that don't require other reactants, but enhance the uptake of some of these species, including glyoxal and methylglyoxal, beyond just their physical solubility. There are radical reactions, which, as it turns out, are mainly important in cloudwater, not as much in the aerosol. And non-radical reactions with ions, which logically are more important in the aerosol because these ions are at much higher concentration and oxidants are at a lower concentration. I'll emphasize that if we were to write down a list of all the chemical reactions taking place in the aqueous phase for aqueous aerosol, cloud droplets, and fog, that list of reactions would be the same because they're taking place in all these media. However, because the chemical conditions of cloud, water, aerosols, and fog are different, the processes that dominate will be different. This is just an overview of some of the updates that have been made to GAMMA through the course of our work since its original publication. Mainly expanding the chemistry, definitely expanding the inorganic chemistry, but also getting more detailed with the pH chemistry, aerosol-cloud cycling, and others. Okay, so this is an overview of the understanding of cloud water processing of volatile organic compounds. So the concept is that cloud droplets have a relatively high concentration of oxidants in them, like OH, and once volatile organic compounds like glyoxal are taken up into the cloud water, they're oxidized and leave behind various organic acids, which have lower volatility than the parent compounds. These reaction pathways are complex, and the product speciation is a little bit complex as well. This chemistry was first proposed and identified, I would say, by Barbara Turpin's group and a few others in the early 2000s. Now, aerosols are a different story. In general, the oxidant levels in aerosols are much lower because all the other solutes in the aerosol are at much higher concentrations. There are also much higher concentrations of ions to take part in reactions such as the processing of isoprene epoxydiol by nucleophilic substitution with various ion species. And so therefore, those kinds of reactions dominate in the aerosol phase, not the oxidation. So this was chemically interesting and not necessarily what people were expecting when we first did this study. But the other thing that came out was that really there's only two pathways that dominate the mass formation of secondary organic aerosol in aerosol water. It's this IEPOX family pathway and the glyoxal family pathway. And that very complex organic aerosol, the organic acid formation from oxidation, that complex family of pathways is relatively unimportant. And so we saw an opportunity to develop a very simple representation of aqueous SOA formation and aerosols that could open up the door for these processes being represented accurately in large-scale models. And so this is what we did with our model simpleGAMMA. It's simply a version of gamma which only contains those pathways which I mentioned in the previous slide are important. And if you check out our 2015 paper, you can see that the fidelity in terms of the mass predictions of aqueous SOA is really great. We're able to reduce all of this down to 4 or 5 lines of Fortran code, which made it simple to integrate with models such as WRF-Chem. So Manish Srivastava from PNNL, the Pacific Northwest National Lab, has done great work integrating simpleGAMMA into WRF-Chem and simulating IEPOX and glyoxal secondary organic aerosol with that, including in our recent Nature Communications paper focusing on the Amazon. We also ended up using simpleGAMMA for some analysis of field data. So having a simple model, besides considerations of computational expense, can also be very convenient when you have field data with a relatively limited set of tracers. So this made it very convenient for interpretation of data from the SOAS 2013 field campaign and others. Other approaches that we're taking for reducing the complexity of aqueous chemistry and representing it in large-scale models include parameterization of the oxidation chemistry. And we're just starting a new project that's looking at automated chemical reduction mechanisms. For the remainder of my talk, I want to focus on a recent study we did looking at the Aerosol-Cloud life cycle and how that can influence aqueous secondary organic aerosol formation. So I thought this might be of interest to you because this was focused on a mountain scenario. So it was emerged out of a collaborative effort related to the Whiteface Mountain Observatory, which is in upstate New York, a bit north of us in New York. And we have 2 scenarios depending on what time of day the cloud is appearing. So we have either aerosols with no cloud or cloud. And in the second simulation, the cloud is appearing in the middle of the day, and then we have significant aerosol processing before and afterwards. We're studying the impact of the aerosol pH as well as the cloud pH within the range that would be typical for Whiteface Mountain, which in previous years had quite a bit of sulfur pollution, so the cloud water was more acidic, but these days it's becoming less so. Okay, so this is a bit much to go into given the amount of time that I have, but I would say a few major takeaways include that the aerosol by the end of the day, when there's both cloud and aerosol processing, has a signature of both phases. So the aerosol ends up having significant organic acids in it, even though they wouldn't be formed during the aerosol mode, right? They're formed during the cloud phase. However, there's another interesting thing about this is that isoprene epoxydiol secondary organic aerosol formation does seem to occur in cloud droplets as long as the cloud is acidic enough. And until I would say 1 or 2 years ago, this wasn't believed to be possible because it was believed that you needed to have extremely acidic conditions for IEPOX secondary organic aerosol formation to happen, for that epoxide ring to be opened. This represents the data in more of a summary version, which you could think of as a little bit more model agnostic. And essentially, if the cloud is acidic enough, you can think that IEPOX SOA formation is pretty efficient, regardless of what's happening in the aerosol. And if the aerosol and the cloud, neither one is particularly acidic, so this would be like a more pristine region with relatively little sulfate or other acid gases around, then we don't also have to worry about IEPOX secondary organic aerosol formation. Okay, so I hope that I've given you a flavor of the efforts we're making to bridge the gaps between the molecular level information that's constantly being generated in laboratory studies by us and by others, and the large-scale models where we need to represent these processes faithfully, but we need to be clever about how we approach that. Okay, with that, I want to thank my wonderful research group, past and present, my funding sources, and all of my collaborators in the Clean Air Toolbox for Cities project. And thank you very much. Have a wonderful conference.